Hello everybody, welcome into another lesson. So today we're going to talk about similar triangles. Well, really for the next 3 lessons we're going to talk about similar triangles. Today there is only one new postulate to learn. This is called the Angle-Angle Similarity Postulate, otherwise known as the AA Similarity Postulate. And it states that if 2 angles of one triangle are congruent to 2 angles of another triangle, then the 2 triangles are similar. So, to illustrate that here, I have triangles ABC and DEF. Well, in the first triangle, angle B is congruent to angle E of the second triangle, and then angle C is congruent to angle F of the second triangle. By that postulate, we can conclude that triangle ABC is similar to triangle DEF. And if we stop and think about this with a triangle, if we have 2 sets of congruent angles between the 2 triangles, then obviously the third angles would have to be congruent, right? Because for any polygon to be similar, all the angles have to be congruent. Well, the sum of the measures of triangle add up to 180 degrees, so the third angles would have to be congruent then. That just kind of makes sense. So, this theorem only works for triangles. It doesn't work for all polygons. It only works for triangles. And then we have some exercises to illustrate that. Should not be a super long lesson today. I know it's Halloween, and by the way, happy Halloween everyone, but I will do some exercises here to illustrate what I'm talking about. So, let's put up a couple triangles here. I'm going to put up some triangles. These aren't exactly the best drawn, but you get the point. So, let's see, this angle here is 40 degrees. This angle here is 50 degrees. Alright? So we have 2 triangles that are right triangles, one with a 40-degree angle, one with a 50-degree angle. We have to determine, are these 2 triangles similar or not? We are basically going to put the angle-angle postulate into practice today. Well, we know that there's 90-degree angles that are congruent. 40 and 50 definitely aren't congruent, but what if we solve for the missing angles? That might aid us. What if we solve for the missing angles? Well, what do we know about the acute angles of a right triangle? That they're complementary. So if you subtract 40 from 90, you'll get the missing angle here is 50. And then right away we can stop because we have 2 congruent angles between the triangles. So, yes, these are similar. These 2 triangles would be similar because both the right angles and then you have 2 50-degree angles between the triangles. So, yes, these 2 triangles are indeed similar by the angle-angle postulate. Alright, what's next? Alright, let's fill in the angle values here. This angle here is 61 degrees. This angle here is 60 degrees. And then in this triangle, you have a 60-degree angle here. You have a 59-degree angle here. Well, we definitely need to solve for the missing angles, right? Because all we can determine is that we have a 60-degree angle in each, which makes one of the angles congruent. So I tell you what we're going to do for now. We'll call the missing angle of the first triangle X. We'll call the missing angle of the second triangle Y. We'll assign a variable temporarily. And we know that the sum of the measures of the interior angles of a triangle equals 180. So let's start with the first one here. If we take x plus 60 degrees plus 61 degrees, we will set that equal to 180 degrees, which then would turn into x plus 121 degrees would equal 180 degrees, which would then have to mean that x equals 59 degrees. So we found the value of x now to be 59 degrees. Well, what do you know? Both triangles now not only have a 60-degree angle, they both have a 59-degree angle. So yes, these two triangles are in fact similar. So by the angle-angle postulate, we can conclude that these two triangles are in fact similar. All right, what's next? This is a good one here. This will bring up some past theorems. All right. So what do we have here? We have that this line is parallel to this line. And that's all they give us to start with, all right? So we have two parallel lines here. So basically you have one triangle split into two. You have a smaller triangle inside of the whole triangle. Both bases are parallel to each other. Well, what do we know about parallel lines cut by a transversal? That corresponding angles are congruent. So this angle here would be congruent to this angle here, since corresponding angles are congruent, which would have to mean then that this angle here would be congruent to this angle here, since corresponding angles are also congruent. So right away, both triangles have two congruent angles, so yes, these two triangles are similar to each other. Or if you wanted to, what you could have done is just found one of these angles, either one, to be congruent to the other, and then used this angle here as a second angle to be congruent in both triangles. Either way, you really have three ways to use the AA postulate to show that these two triangles are in fact similar. Okay, so what's next? Let's see. So we get with this triangle that we have a 42-degree angle, and this side's congruent to this side. In this triangle, we also have a 42-degree angle, and this side is congruent to this side. So what do we know about isosceles triangles? That the angles opposite those sides are congruent to each other, okay? But we don't know the angles, so we'll call this angle x. We'll call both of those x since they're congruent. We'll call both of these angles here y since they're both congruent. The isosceles triangle theorem applies to both of these triangles. Now, what we have to do here, we need to find the measure of x. So we'll take x plus 42 degrees, set that equal to 180 degrees, which would then give you that 2x plus 42 equals 180 degrees, which would then give you the fact that 2x is equal to 138 degrees, which could only mean then that x equals 69 degrees. So now we can identify that both of these angles in this isosceles triangle have 69-degree angles. Okay, so what about this one? Well, if you really look at it, it wouldn't make a difference if we put in y. Let's solve for y. Because you have 42 degrees as the third angle in the other triangle, so let's do y plus 42 equals 180. Well, that would just give you 2y plus 42 equals 180. And then 2y equals 138, meaning also that y equals 69. So both of these angles are also 69 degrees. So right away, we notice two congruent angles. This is another one where you have three ways to use the AA Similarity Postulate to prove that these two triangles are in fact similar. So yes, these two triangles are in fact going to be similar. All right. So, I mean, I think the AA Similarity Postulate's pretty simple to understand. If you have two congruent angles of one triangle congruent to... If you have two angles of one triangle congruent to two angles of another triangle, then they're similar. Let's see. Now, here's a good one. Oh yeah, this is going to be a good one. Now, in each of these triangles, they give you that two of the sides have a length of 5. That's all they give you. Well, it would seem to be that the isosceles triangle theorem comes into play, right? So this angle here would be congruent to this angle here, and then the second triangle, this angle here would be congruent to this angle here. But here's the problem. We don't know anything about the third angle of these triangles. We know nothing about it. We don't even know anything about these two angles. We don't know if they're congruent or not. They could have different angles. So in this case, there's no conclusion. There's actually no conclusion. We can't rightfully conclude if both of these triangles are similar or not, because we don't know anything about the angles themselves. We just know we have congruent angles in each triangle, but we don't know if they're congruent to each other or not. So there's no conclusion for this one. All right. Very interesting one here. Very interesting indeed. So, what about these two triangles? So, you basically have one big triangle that, well, honestly is split into a triangle and a quadrilateral. So what this is going to end up being is the small triangle inside of the big triangle similar to the whole triangle? Is the small triangle similar to the whole triangle? That's really what we're going to try to ascertain. Well, both the small triangle and the whole triangle have a right angle. They got that going for them, right? However, look at this angle up here. Don't both the small triangle and the whole big triangle share this angle? You actually have two angles that are congruent, so yes, these two triangles are in fact similar to each other because you have two congruent angles. So by the AA Similarity Postulate, these two triangles are in fact similar. Alright, what do we got here? Another interesting one. Then how do they draw that? Yeah, that looks odd, I know, but bear with me a second, okay? Alright. So we have two right triangles next to each other, right? They're literally stacked right next to each other. They connect each other, in fact. Well, they both have a congruent right angle, since they're right triangles. That much is going. But we notice here we have another set of congruent angles between the two. So, yes, these two right triangles are, in fact, similar to each other. So we can actually, in this case, use the AA Similarity Postulate to show that these two triangles are similar. Alright, I have 3 more exercises, then we're done for the day. These are different, though. The next 3 exercises, we will have similar triangles, so it will be established that we have similar triangles. All right. So this line is parallel to this line. What else do we have? This has a length of 9. This has a length of 3, making the whole length of this segment equal to 12. This is 8. This is x. This here has a length of 12. This here has a length of y. Then together, this whole segment here has a length of y plus 12. Okay? So the goal is we are going to solve for x and y. We do have 2 similar triangles. Well, if we remember yesterday, because what we're going to do is we're going to compare the smaller triangle to the whole triangle. So the smaller triangle in this region is similar to the whole triangle that it's inside of. First thing you probably want to do is find your scale factor. Remember, whenever you have similar triangles, you want to find the scale factor for your sides. So this 9 here in the smaller triangle is to the 12 for the whole side of the whole triangle. Well, 9 to 12 turns into what? 3 to 4. So we've identified 3 to 4 as our scale factor for these 2 triangles. So 3 to 4 is the scale factor, referring to the denominator of 3, which comes first for the smaller triangle, and then 4 for the numerator of 3, then the denominator 4 for the whole triangle. So now we need to solve for x. So in order to do that, you'll take your scale factor of 3/4, and then since we have the smaller triangle first, you'll have that equal to x over the 8 for the whole triangle, which now we cross multiply. You would end up getting 4x equals 24, which means that x equals 6. So the value of x would in fact be 6. Okay, now the next one's going to be fun. The reason I say that is because we still want to solve for y, but take your scale factor of 3 to 4. You're going to set that equal to, in the numerator, 12 for your smaller triangle, over the y plus 12 for the side of the whole triangle. So now we don't just simply have y by itself, we have y plus 12. Well, let's do the cross product. You'll end up having 3 times y plus 12 is equal to 48. I'm going to move over here. 3 times y plus 12 equals 48, which would just give you y plus 12 equals 16, which would then give you that y equals 4. So the values you should come up with are that x equals 6 and then y is equal to 4. Now it's good we get a little bit of review in from yesterday. All right, what do we got here? Another one like it. Alright, so once again, we have a smaller triangle inside of a bigger triangle, and these triangles are similar, okay? So, since they're similar, first thing you want to do is find your scale factor. Well, a couple things to note first, okay? The smaller triangle for this side has a length of 4. If you want to find the length of this side of the whole triangle, you're going to add the 4 and 2 together, which let me illustrate that here real quick. 4 plus 2, that gives you a length of 6. Alright, so this smaller length 4 in ratio to the whole length of 6, that turns your scale factor into 2 to 3. So 2 to 3 is your scale factor. So now we want to solve for x. Well, take your scale factor of 2 to 3. So the numerator is for the smaller triangle first to the denominator of the whole triangle. So in this case, if we're going to solve for x, the corresponding side is 6, which should go in the numerator. Then your denominator would be x for the whole triangle. Do your cross product, you'll end up getting 2x equals 18, which would then give you that x is equal to 9. So the answer is then that for x, that it equals 9. Now we got to figure out y. So we've established our scale factor, but once again, our goal is to solve for y, isn't it? Here's the problem though. The y is going to be in ratio to the whole length of this side. If you add the whole side together, what you're going to get is the length of this whole side is actually y plus 3. That's the length of the whole side is y plus 3, okay? Well, still take your scale factor. That's going to be 2 to 3. That's going to be equal to the length of this side here for the smaller triangle, which is just simply y, over the length of the whole side for the whole triangle, which would be y plus 3. So now you have a variable in both the numerator and denominator of the second ratio. Well, take your cross product. You'll have 2 times the quantity of y plus 3 equal to 3y, which would then give you that 2y plus 6 is equal to 3y, which could only mean then that y is equal to 6. So the answers you should get are x equals 9 and then y equals 6. And I have one more exercise, then we're done for the day. Okay, I think that's good enough. Another one with a smaller triangle inside of a whole triangle. This has length 12. This has length 4. This has length 15. This has length y. This has length x. This has length 12. Okay. So now we've established our lengths. Well, what we have here then, we have a smaller triangle inside of a whole big triangle. So we're going to, they are similar triangles, of course, but we have to compare the scale factor of the smaller triangle to the whole triangle that it's inside of. Well, let's start with something here. The only place we have both numbers is on this side here, right? So the length of this whole side would be 16 if you add the 12 and 4, right, for the whole triangle. So now what you have to do is take the ratio of the smaller side, 12, to the whole side of 16. Well, 12 to 16 would reduce to 3 to 4. So 3 to 4 is your scale factor. So now that we've identified our scale factor, we're in business. Now, of course, we want to solve for x to start. So you'll take your scale factor of 3 to 4, set that equal to, since we started with the smaller triangle first, that'd be equal to x in the numerator over the corresponding side of the whole triangle, 12 in the denominator. Which then you do the cross product, you get that 4x equals 36, which would then give you that x equals 9. So the length of x in this case should be equal to 9. Now we got to solve for y. Okay. Well, again, to solve for y, we got to find, ultimately, it's going to be the ratio of this length of 15 to the whole length of this whole side, which would give you that this side here would be y plus 15. This whole side is actually y plus 15. So let's solve for y. What you'll get then is your scale factor of 3 to 4 still. That'll be set equal to the smaller side of 15 for the smaller triangle, all over the length of the whole side for the whole triangle, which would be y plus 15. So then now you're going to take your cross product. You'll take 3 times y plus 15, that quantity, set that equal to 4 times 15, which is 60, which then you factor out a 3 from both sides, divide both sides by 3, you should get that y plus 15 is equal to 20, which then should just give you that y is equal to 5. So the answers you should get are that x equals 9 and then that y is equal to 5. So that's it for this lesson. Next lesson we're going to have 2 theorems about similar triangles that are also very interesting. So I hope everyone has a good night. Happy Halloween. Take care.